Hello everyone. This video was made because I always wanted to measure the performance between virtual machines and Linux containers in Proxmox. I wanted to see what happens if you run the same workload inside a virtual machine versus an LXC container, and how much performance do you actually leave on the table with the VM. And to be honest, the results completely surprised me. At one point, the container was 10 times faster than the virtual machine on the exact same hardware, and it took me a full investigation to figure out why. So let's get into it. Quick background if you are new to Proxmox. Proxmox VE is a hypervisor. It's the software that sits on bare metal and lets you run virtual machines and containers side by side on the same host. A virtual machine or VM is a fully emulated computer. It has its own kernel, its own virtual hardware, virtual CPU, virtual network card and virtual disk. The hypervisor intercepts all that hardware access. It's complete isolation, but there is overhead. An LXC container is different. LXC stands for Linux containers. Instead of emulating hardware, it shares the host kernel directly and just gets its own isolated file system, network namespace, and process space. Much lighter weight, much closer to bare metal. But the trade-off is you don't get the same level of isolation as a VM. The question is, how much does that isolation actually cost? My test setup: an AMD Ryzen 9 7950X, so a Series 16 core 32 thread desktop CPU. Both the VM and the container got 16 vCPUs and 16 GB of RAM. Storage is ZFS on NVMe. I'll explain what that means in a moment. And networking is 10 Gigabit Ethernet between this machine and another physical machine, which we will use for the network tests. You're going to hear ZFS a lot, so let me quickly explain why it matters here. ZFS is a file system, but it also handles storage pooling, checksumming, compression and snapshots all in one. The relevant detail for this video is how ZFS stores data on disk. ZFS doesn't write your files directly in the size you gave it. It works in fixed size blocks. If your block size is 16 kilobytes and you write a 4 kilobyte file, ZFS still writes a full 16K block. That 4:1 ratio is called write amplification. You write 4K, the disk does 16K of actual work. For the VM, the disk is a ZVol, a ZFS volume, basically a raw block device. Its block size is called vol block size, and I set it to 16K. For the container, the file system sits directly on a ZFS dataset. Think of it as a directory managed by ZFS. Its equivalent setting is called record size. By default, that's 128 kilobytes, but I changed it to 16K for the second round of tests, specifically to make the comparison fair. Same write amplification on both sides. And that matters a lot, as you will see. So I ran the first round of benchmarks and the results looked suspicious. For the CPU, I used Sysbench, which is a common benchmarking tool. Single-threaded CPU performance was essentially identical between the VM and LXC. Makes sense, there's no reason it should differ. But multi-threaded performance was also basically identical, which actually shouldn't be the case. That was my first red flag. Turned out I had configured Sysbench to use 32 threads on a machine with 16 vCPUs. When you have more threads than cores, the OS has to context switch between them, which adds overhead. Both VM and LXC were getting hit equally, so the scores looked the same, but the numbers were inflated garbage. Easy fix: match threads to vCPU count. For storage, I used FIO, which is the standard tool for measuring disk I/O, but I was using it wrong. I had it configured with psync as the I/O engine and I/O depth set to 1. I/O depth controls how many I/O requests are in flight at the same time. With depth 1, you fire off one request, wait for it to complete, then fire the next. NVMe drives are designed to handle hundreds of requests simultaneously. Running them single file is like having a 16-lane highway, but only letting one car on it at a time. My random IOPS numbers were about 100 times lower than reality. For networking, I used iPerf3, which measures network throughput, but I made a classic mistake. I ran it from one container to another container on the same physical host. No packets ever hit a real network card. I was just measuring how fast data moves through kernel memory, which is fast but not useful. And the UDP test had the -B 20G set that's telling the sender to push 20 gigabits per second at a receiver that can only handle 3. Predictably, 53% of packets got dropped. So, round 1 was mostly a collection of methodology mistakes, but finding the mistakes was the point. Let me walk you through the corrected results. After fixing everything, correct thread count, libIO engine with IO depth 32 and 4 parallel jobs, iPerf3 running between 2 separate physical hosts, here is what happened. CPU and memory, basically a tie. Single-threaded performance is within 0.6% of each other. Multi-threaded, the VM came out about 19% ahead, but I suspect that's scheduling noise rather than a real architectural difference. But it is faster nonetheless. Memory bandwidth is effectively identical. This confirms what most people would expect. For pure computation, VM overhead on modern hardware is negligible. Network, also essentially a tight throughput, both capped at about 3.2 gigabits per second. The ceiling isn't the VM or the container, it's the switch. My switch has two identical SFP plus 10 gigabit ports, and the internal fabric seems to throttle traffic between them. The interesting finding here is the TCP retransmits. The VM had 86,000 retransmits during the test, while the LCX had 125. Same throughput, but the VM's VirtIONet multi-queue setup was pushing the NICs hard enough to stress the switch, causing instability. The LXC's simpler vEth bridge just naturally rate limited itself. The UDP test was also revealing. The VM's VirtIONet with 4 queues pushed to 6.9 gigabits per second at the sender, but the single-threaded receiver could only handle 3.3. So 53% packet loss again. The LXC naturally kept its send rate at 3.2 gigabits with zero loss. Unix bench. The VM scored about 85 to 115% higher. This one surprised me at first until I looked at which subtests were driving the score. Dry stone and wet stone. Pure CPU math were identical. The composite score was dominated by file copy tests, which are IO bound, which brings me to storage. So what about the storage? This is the one that got me. Sequential reads and writes. The VM wins significantly. Sequential read. The VM got 1186 megabits per second versus the Linux container 889. Sequential write. The VM got 1219 versus the LCX 587. The VM is about twice as fast on sequential writes. That part makes some intuitive sense. The ZWall block device has less overhead for large sequential I/O. Random reads. The VM crushes it. 289,000 IOPS for the VM and 38,700 for the LXC. That's a 7.5 times difference. The VM's direct block device access is much better suited for random reads at depth. And then random writes. VM 4,624 IOPS and LXC 50,200 IOPS. The container is 10.9 times faster than the virtual machine on random writes. and both sides are using 4K writes with O-Direct on ZFS with matching 16K block sizes. Same write amplification, same hardware, but the LXC just absolutely destroys the VM here. This was counterintuitive enough that I had to go investigate. The key is what O-Direct actually means in different contexts. O-Direct is a flag you can pass when opening a file. Normally, Linux uses a page cache. When you write something, it goes into RAM first and the kernel flushes it into disk later in batches. O-Direct bypasses that cache and goes straight to the storage layer. On the VM's volume, O-Direct means truly bypassing everything. The write goes directly to the ZFS block device. And because this is ZFS, each write triggers a copy on write operation. ZFS never overwrites data in place, it always writes to a new location and then updates the pointer. For a 4K write on a 16K block, that means reading the old 16K block, modifying 4K of it and writing the new 16K block. Plus, with sync pressure, ZFS occasionally has to flush a transaction group, a batch of pending writes, to disk synchronously. The FIO results showed max latency of 101 seconds for some IOs. That's not a typo. On the LXC's ZFS dataset, O-Direct bypasses the Linux page cache, but the writes still go through the ZFS ARC, which is ZFS' own internal cache. More importantly, they still go through ZFS's transaction group mechanism, or TXG. ZFS batches writes into transaction groups that it commits every 5 seconds by default. So even though you said O-Direct, ZFS is quietly coalescing your writes and flushing them asynchronously. It looks like it's bypassing caching, but it's not. To prove this, I ran 3 more tests on the LXC. First, without O-Direct at all. No direct. Result 37,200 IOPS. Actually slower than O-Direct's 50,200. That's because with no direct, you get double buffering. Linux page cache and ZFS ARC both trying to manage the same data, adding overhead. Second, with fsync equals to 1, which forces a sync call after every single write, bypassing TXG batching. Result is 2116 IOPS, worse than the VM's 4624. The VM actually wins here. Third, with sync set to always, a ZFS level setting that forces every write to commit immediately. Result was 900 IOPS. So, when you force the LXC to behave the same way the VM behaves, sync on every write, it's actually worse than the VM. The zvol's sync path turns out to be more efficient than the dataset sync path. The 50k IOPS we saw was entirely the result of ZFS batching writes in the background. It's fast, but it's also somewhat deceptive as a benchmark number. That performance doesn't exist if you need guaranteed durability. So, what does this all mean? If you're running compute workloads, CPU-heavy tasks, in-memory processing, VM versus LXC makes almost no difference on modern hardware. The overhead is negligible. If you care about raw sequential storage throughput, the VM wins. The zvol block device has less overhead for large sequential I/O. If you're running a database or anything that uses buffered writes, and most do, the LXC will look spectacularly fast in benchmark. But that speed comes from ZFS batching, not from the container being fundamentally fast. If your workload requires fsync after every transaction, you'll get VM level performance or worse. Network is a tie on throughput, but the VM's multi-queue networking is more aggressive and less stable when the downstream switch can't keep up. And the big meta lesson: how you configure your benchmarks matters enormously. Wrong thread counts, wrong FIO engines, wrong IO depth, running iPerf on the same host, all of these produce results that look plausible but were measuring the wrong thing entirely. If you are benchmarking anything, sanity check your methodology before you publish the numbers. All the slides and benchmark scripts from this video are linked below. Thanks for watching.